Assalamualaikum warahmatullahi wabarakatuh and very good day to all of you. Okay, for chapter number 3, part number 5, we will discuss about compressor cascade correlations. So we will learn about the equation or the correlation that obtained from the compressor cascade investigation. Okay, about the compressor cascade correlations by Howell 1942 and also 1945. Okay, for Howell 1942, the low speed correlation of Howell 1942 has been widely used by designer of axial compressor. So the graph shows the one of the result that obtained by Howell 1942, and this graph we already discussed when we discussed about the off design performance for the compressor cascade. Okay, so based on this graph, I will explain about the few correlation that introduced by Howell. So the first correlation that introduced by Howell in 1942 is the correlation that based on the design point as shown in the figures. So design point for this graph, which is referred to the relative deflection angle value. At design point, the value of the ratio 0.8 multiplied by stalling deflection angle divided by nominal deflection angle equal to 1.0. So if you refer to the original equation, so at the design condition, we will have the first equation correlation, the first correlation that introduced by Howell, which is the correlation for nominal deflection. So nominal deflection angle equal to 0.8 multiplied by stalling deflection angle. Okay, for the second correlation, the correlation is based on the stall point condition as shown in the figure. So normally at the stall point condition, the value of stalling deflection angle more or less equal to the value of maximum deflection angle. So that's why we have the correlation in this graph where 0.8 epsilon s divided by nominal deflection angle more or less equal to 0.8 maximum deflection angle divided by nominal deflection angle equal to 1.25. So if you refer to the original equation at stall condition, so we have the second correlation where the second correlation mentioned that the stalling deflection epsilon s or stalling deflection angle equal to 1.25 multiplied by nominal deflection angle. Okay, so this equation, see this correlation is independent of blade camber angle, where theta, the blade camber angle, theta equal to alpha 1 prime minus alpha 2 prime, as shown in the schematic diagram of the cascade blade, where the camber angle actually the angle between trailing edge line and also the leading edge line, as shown in the figure. So for the value of camber angle between 20 degree and 40 degree, so this correlation is still valid. So no problem. There is no problem if we implement the second correlation where epsilon star equal to 1.25 nominal deflection angle within the camber angle value between 20 degree and also 40 degree. Okay, next, the correlation that is done by Howell in 1945. So Howell investigated the nominal deflection for various compressor cascade, and he obtained correlation between nominal deflection angle against the outlet flow, nominal outlet flow angle alpha 2 star. Okay, as shown in the figures. So the graph actually shows the general exists for the variation of nominal deflection with nominal outlet angle for several space chord ratio graph. So there will be the correlation between nominal deflection angle and also nominal outlet angle for specific value of space chord ratio. So Howell mentioned that the nominal deflection angle actually is a function of S over L, chord space distance divided by chord length, and also the the value of nominal deflection angle also affected by the value of alpha 2 star, the outlet flow angle, nominal outlet flow angle, and also the last one is the value also affected by the Reynolds number value. Okay. However, for the specific S over L, the dependence on Reynolds is small for Reynolds number greater than 30,000. As we know, for Howell investigation, the flow condition in terms of Reynolds number is around 30,000. Okay, so in the graph we can see that the Howell provide three type of curve based on S over L value. So we have S over the curve for S over L equal to 0.5, S over L 1.0, and also S over L 1.5. So from this graph, if we have specific value of S over L and also the value of nominal outlet angle, so we can determine the specific value of nominal deflection angle in order to determine the the efficiency or the performance of the cascade compressor cascade blade. Okay, for this third correlation, so based on the figures of variation of nominal deflection with nominal outlet angle, we will have the third correlation that can be used for preliminary performance estimation. So this equation we can use to reduce time for analysis in order to simplify the analysis process in the compressor cascade investigation. So if we refer to the angle value of alpha 2 star, the nominal outlet angle between 0 degree and also 40 degree. So within this region, we can use a correlation that we call tangent difference rules that represent by this equation, where the equation mentioned that tangent alpha 1 star minus tangent alpha 2 star equal to 1.55 divided by 1 plus 1.5 multiplied by S over L, where alpha 1 star actually is the nominal inlet flow angle and alpha 2 star is the nominal outlet flow angle. So now, so from this slide we have three different correlation that introduced by Howell. Okay, for this slide, compressor cascade correlation, so I will introduce the fourth correlation that introduced by Howell 1942. So Howell introduced the nominal deviation angle equation for delta star. So the figure shows what I call the simplified wind tunnel schematic diagram for cascade blade investigation that consists of a fan, a straighteners, and also the cascade section. So normally during the investigation, okay, the condition at the inlet already decided by the designer or by the researcher. So for example, what I call the value of fluid flow velocity C1 as shown by the pink color arrow, and also the angle of fluid flow angle alpha 1. So normally this value, inlet fluid flow velocity C1 and also angle inlet fluid flow angle alpha 1, normally already determined by the designer or by the researcher during the experiment. So in order to change the value of C1 and also alpha 1, so we can change the fan speed and also the cascade angle. Okay, the other parameter is I, the incident angle, which is the angle between the fluid flow velocity vector and also the leading edge line. So we'll get the angle for incident angle. And the incident angle also normally already decided by the researcher or by the designer in the cascade blade investigation. Okay, order if we want to change the value of incident angle, we can change the cascade blade angle, cascade angle, which is referred to the cascade section angle. And normally we already know the value of incident angle. So if you look at the schematic diagram of the cascade blade, so the value of I, incident angle, is controlled or determined by the designer or by the researcher. Okay, however, at the outlet condition, such as the value of C2, the outlet fluid flow velocity, alpha 2, the outlet fluid flow angle, and also the deviation angle are unknown parameter. So this parameter is not known. So we need to determine by using this equation, by using the specific sensor, or we need to estimate by using specific correlations. Okay. So Howell suggests try to estimate the deviation angle by using a specific correlation, where we know that the general definition or equation for deviation angle delta equal to alpha 2 minus alpha 2 prime. So as we know, Howell already mentioned that the nominal deflection angle actually is function of S over L ratio, alpha 2 star value, which is referred to the nominal outlet flow angle, and also Reynolds number. So that's why the value of deviation angle is important, because of the value of alpha 2 star, as mentioned by Howell. Because in general equation for delta also will have the parameter of alpha 2, the outlet flow angle. Okay, so the deviation angle is an important design parameter that depend on the blade chamber, blade shape, S over L ratio, and also the stagger angle. So for nominal deviation angle, Howell suggests the correlation for nominal deviation angle to the camber and also space chord ratio, as shown in this equation, where nominal deviation angle delta star equal to m multiplied by theta multiplied by bracket S over L power of n, where m refer to this equation, where this value of m depend on the camber line and also blade setting, and we can obtain the value of m by using this equation, where m equal to 0.23 multiplied by bracket 2a over L square plus bracket alpha 2 star divided by 500. However, the value of n for the compressor cascade, the value will be fixed at more or less equal to 0. Approximately, the value of n is approximately equal to 0.5. We just substitute with n value equal to 0.5 in the equation. Okay, so estimated deviation, this equation will give us the estimated deviation delta star, where this is the important quantity for design in terms of compressor blade. Small error in delta star, estimated deviation angle, nominal deviation angle, will cause large change in deflection angle, nominal deflection angle. As we know that nominal deflection angle or deflection angle will have direct impact to the value of compressor cascade efficiency. So large change in deflection, nominal deflection angle, will cause large change in predicted performance mu for the compressor cascade. Example 3.8. A compressor cascade has a paste chord ratio of 1.5, and blade inlet and outlet angles of 40 degree and 15 degree respectively. If the blade camber line profile is A over L equal to 25%, and the cascade is designed to operate at Howell's nominal condition, determine the fluid deviation, fluid deflection, incidence, and ideal lift coefficient at the design point. So you can use the figures as your reference to answer the question. Okay, solution for example 3.8. So that data given in the equation are n equal to 0.5, s over l equal to 1.5, alpha 1 prime equal to 40 degree, alpha 2 prime equal to 15 degree, and the last one a over l equal to 0.25. From general equation of deviation angle and also nominal deviation equation, so you will get equation number 1 where delta star equal to m theta multiplied by s over l power of n, and also equal to alpha 2 star minus alpha 2 prime. Parameter m in equation 1 is equal to m equal to 0.23 multiplied by 2a over l square plus alpha 2 star divided by 500. Substitute the value of a over l into the equation, so you'll get equation number 2 where m equal to 0.0575 plus 0.002 alpha 2 star. Camber angle theta in equation number 1 can be determined by using the general equation for the camber angle, and also the value is equal to theta equal to alpha 1 prime minus alpha 2 prime equal to 25. Equation number 3. Substitute equation 3 and equation 2 into equation number 1. Equation for nominal outlet flow angle can be determined. Okay, m theta s over l power of n equal to alpha 2 star minus alpha 2 prime. Okay, so the value, substitute all the value obtained. So alpha 2 star equal to 17.85 degree. From general nominal deviation equation, equation number 1, delta star equal to alpha 2 star minus alpha 2 prime. So we know that the value of alpha 2 star equal to 17.85, alpha 2 prime equal to 15. So you'll get the value for nominal deviation angle, which is equal to 2.85 degree. So for nominal deflection angle value, in order to determine the nominal deflection angle value, epsilon star, we need to use the graph where the value of s over l equal to 1.5, alpha 2 star equal to 17.85 degree. So by referring to the graph shown in the slide, so we already have the value for delta 2 star, and also we need to refer to the graph of s over l equal to 1.5, the pink color curve. Okay, find out the intersection between the vertical line with the vertical line at the alpha 2 star at 70.85 intersect with the line for s over l equal to 1.5. So we can get the nominal deflection from the graph where the value of nominal deflection angle is more or less equal to 20 degree. Okay, from general deflection angle equation, nominal inlet flow angle alpha 1 star. Okay, so we can use the deflection angle from the deflection angle equation. So epsilon star equal to alpha 1 star minus alpha 2 star equal to 20 degree. So from the equation, we can determine the value of alpha 1 star, because alpha 2 star we already obtained from the previous question. So alpha 1 star equal to 37.85 degree. From general incident angle equation, nominal incident angle I star can be determined where I star nominal incident angle equal to alpha 1 star minus alpha 1 prime, which is equal to negative 2.15 degree. For nominal ideal lift coefficient, we need to know that for the ideal case, CD value will be equal to 0 because we neglect the effect of drag force or drag coefficient. So from lift coefficient equation, as shown in the slide, CL equal to 2 S over L cos alpha m multiplied by bracket tangent alpha 1 minus tangent alpha 2 minus CD tangent alpha m. So the term for CD tangent alpha m we can neglect due to the value of CD equal to 0 for the ideal case. From mean flow angle equation, nominal mean flow angle is alpha m star equal to 28.79 degree. Thus, nominal lift coefficient equation as shown in the slide, where CL star equal to 2 multiplied by S over L cos alpha m star multiplied by bracket tangent alpha 1 star minus tangent alpha 2 star. So substitute all the value that we already obtained into the equation. So we'll get the final answer for CL, nominal lift coefficient, which is equal to 1.19. Okay, in order to test your understanding about this part number 5, chapter number 3, answer the question below. First question, a compressor cascade blade investigation use a blade profile with S over L equal to 1.0 with nominal outlet flow angle of 30 degree. Determine the nominal deflection angle. Question number 2, by using the tangent difference rules, determine the nominal deflection angle if nominal inlet flow angle is 30 degree and S over L value equal to 1.5. Question number 3, why the deviation angle is so important in compressor blade design. So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue also given in the link. So that's all for chapter number 3, part number 5. Assalamualaikum.